So we are going to talk about atoms, ions, and molecules. And in this particular video, we're going to look at a little bit of the history of chemistry and how we learned about atoms and the parts of an atom. So before we jump into that, a little bit of chemistry humor here for you. So go ahead and take a look at those two jokes before we move to the next slide. So if you look at a periodic table, what you'll find is a whole lot of elements with their symbols and their atomic numbers and some numbers underneath them, and we're going to talk about what all that means if you're not already familiar with it in just a few minutes here. But before we get into that, if we look at a column going up and down, we call that a group. Elements are grouped together the way they are because elements in a group all have similar properties. So they will lose the same number of electrons. They will tend to react in very much the same way. So those are all in a group together. If we go across a row, we call that a period. So as you can see from the color coding here, we have on the left side of the periodic table, the bottom left here, a bunch of elements in green. Those are our metals. If we look at the top right here, we have our non-metals, most of which are gases, although a few of them are liquids. And then along the staircase in pink here, we have our metalloids or semi-metals, which have properties, some properties like metals and some properties that are like non-metals. So if you look at a period, as we go across the period, we have metals, and then we eventually get to the semi-metals, and then we get to non-metals. So it's quite obvious those are not going to have the same properties as each other. But elements that are in a group will have very similar properties. Metals are the category that take up the bulk of our periodic table. They're the elements that are on the left side towards the bottom of the periodic table. If we look back at our periodic table here, those are all the ones that are in green. So metals tend to be shiny solids. They're very good at conducting heat and electricity, and we frequently use them for applications where we need them to conduct electricity or to conduct heat. So things like wiring and our electrical wiring, or on the top of an oven or stove, and we can think of a lot of different applications where we use metals to conduct heat or electricity. They're typically very malleable, which means that we can hammer them out or press them out without breaking them or cracking them. Now you may need to heat them high enough temperatures to melt them in order to do that, but we can do that without breaking them into pieces. They're also typically very ductile, which means that we can draw them out to thin wires, which is pretty useful when we're trying to do things like make electrical wiring. Non-metals are the elements that are towards the right and top of the periodic table. The vast majority of them are gases, although there are a few like bromine that tend to be liquids, and there are a couple that are solids, not very many. Non-metals are non-conductors. They do not conduct heat or electricity very well. The ones that are solid are pretty brittle, which means they tend to break apart very easily. They tend to crumble and just kind of become dust in little pieces, rather than being solids that are easy to they're not very easy to handle. Metalloids we also sometimes call those semi-metals. So as I mentioned, they're between the metals and non-metals. And they have some properties that are like metals. For example, they're typically shiny solids, just like the metals are, but they're very brittle like non-metals. Our metalloids or semi-metals tend to be semiconductors. They conduct electricity, but not very well, not nearly as well as metals do. And sometimes what we'll do for things like silicon, which we tend to use as chips in things like cell phones and tablets and laptops, is we will dope them with a metal, what doping does is it allows the semi-metal or metalloid to conduct electricity better. So the groups on the periodic table have names. Group 1, or 1A, is known as the alkali metals. Group 2, or 2A, is the alkaline earth metals. So be very careful with those. They sound somewhat similar, but they have very different properties. So don't confuse alkali metals with alkaline earth metals. Alkali refers to a base. So those elements, especially in group 1 and also group 2, if you combine them with the hydroxide ion, they form very strong bases. We go over to the other side of the periodic table. Group 18 or 8A is our noble gases. Those are also known as the inert gases because they don't tend to be very reactive. There are a couple of them that do form some compounds, but in general they tend to not be very reactive. Group 17 or 7A is our halogens. Group 16 or 6A is our chalagens. We just add a C to the halogens. So these group names you will want to be familiar with. If you're told that something is a halogen or that something is an alkaline earth metal, you'll need to know which group of the periodic table we're referring to without being told the group. The elements on the larger columns here are our main group elements. So you'll notice if you look at periodic tables, sometimes you'll see two different numbering systems. The older numbering system has these The older numbering system has these taller groups labeled 1 through 8A, and the transition metals here in the center is B. The newer system, which is what IUPAC is designated currently, and IUPAC is kind of the authority in naming elements and rules to do with chemistry things, that we typically designate these columns as 1 through 18. Now the older system does have some uses, as we'll see as we move along. So if you're looking at the older system, we're looking at the A groups. Those are our main group elements. The elements in the middle are designated the transition metals. And we're going to talk later on about why the transition metals are separate. These elements down here are known as the intertransition metals. We don't really deal with those a whole lot, so we tend to kind of ignore those a lot of times in general chemistry, just because we don't really have a whole lot of use for them at this point. But just know those are down there. The reason they're floating down here at the bottom rather than being in the periodic table up here is because if you look at the numbers, 58 starts the first column and 90 starts the second one. So those would fit in right about here. If you put those into the periodic table where they're supposed to be, then what you find out is you're going to have a really long periodic table that's kind of hard to pronounce. So we just kind of move those down to the bottom to make the periodic table a little more manageable so that we can fit it onto a piece of paper when we're trying to print it out to work with it. So let's talk a little bit about the early history of chemistry. So if we go way back into 400 BC, into some very early history here, and we're going to start with the Greeks. The Greeks thought that matter was composed of only 4 substances, and those 4 substances were earth, fire, air, and water. So everything was composed somehow of these 4 fundamental substances, or some mixture of them. Then for about the next 2,000 years, alchemists dominated much of what we knew about chemistry. So we didn't make a whole awful lot of progress here. We did learn a little bit about how chemical reactions work, so we did get something out of that. But if we skip ahead about 2,000 years, we come to Antoine Lavoisier. And around this point, we start making some progress in the field of chemistry. So Antoine Lavoisier was the one who explained the true nature of combustion. Up until that point, people thought that combustion involved some mysterious substance called phlogiston. We're not entirely sure what phlogiston was supposed to be, but it was this mysterious substance that somehow allowed things to burn. And Lavoisier did some quantitative experiments that eventually showed us that combustion involved the reaction of oxygen with whatever you were burning in the presence of heat, and we eventually form, as this substance burns, we form an oxide of that substance. Lavoisier also regarded measurement as the essential operation of chemistry. And I think we would say that that's still very true. We tend to do a lot of math in chemistry, and measuring things is fundamental to a lot of what we do. He also verified the law of conservation of mass. So the law of conservation of mass tells us that mass is neither created nor destroyed in a chemical reaction. We can change it in form. Sometimes we can convert mass to energy, but we cannot create matter out of something that wasn't there to start with, and we can't destroy it. It has to go somewhere and turn into something else. Joseph Proust was the one who defined the law of constant composition. So we talked a little bit about this in the first chapter. The law of constant composition, or the principle of constant composition, is also known as the law of definite proportions. So that law tells us that a given compound always contains exactly the same proportion of elements by mass. So for example, if we take something like water will always have twice as much hydrogen as it does oxygen. If we take something like ammonia, it will always have 3 times as much hydrogen as it does nitrogen. The law of multiple proportions tells us that when 2 elements form a series of compounds, the ratios of their masses can always be reduced to small whole numbers. So for example, if we have something like carbon monoxide and carbon dioxide, the ones that don't have anything written there are understood to be a 1. So we have 1 carbon and 1 oxygen, 1 carbon to 2 oxygens, or we can take something like nitrogen and oxygen, so we can have N2O, we can have NO2, we can have NO, but we would not have something like, we would never have 1.5 oxygens per nitrogen. That's just not possible. So we can always reduce these to small whole numbers. So for example, you can also have N2O4, but you cannot have, okay, that does not exist. So Dalton's atomic theory has 4 components here. So the first component is that each element is made up of tiny particles that we call atoms. The second part of this tells us that atoms of a given element are identical. So we know now that this is not completely true. And if you know what an isotope is, then you know why that's not completely true. If you haven't heard of an isotope before, we're going to define those pretty soon. The third part of this says that chemical compounds are formed when atoms of different elements combine with each other. And it also tells us that a given compound always has the same relative numbers and types of atoms. So we kind of already talked about this. For example, if you have something like water, it always has 2 hydrogens and 1 oxygen. If you have something like ammonia, it always has 1 nitrogen and 3 hydrogens. If you have something like carbon dioxide, it always has 1 carbon and 2 oxygens. You will never have a compound that has a different element or a different number of that element. It will be a completely different compound. And the last part of this is that chemical reactions involve reorganization of the atoms. So when we do a chemical reaction, we don't change the atoms themselves, but we do reorganize them to form different substances. So as we get into some more chemistry and some more history here, we're going to talk about how we learn about different parts of the atom. So J.J. Thomson used what we call cathode ray tubes to study some of the parts of an atom. So what he did was he set up this cathode ray tube, and we have a metal electrode at one end that's negatively charged, and we have a metal electrode at the other end that's positively charged. And then we have this partially evacuated glass tube here that's partially under a vacuum. And a cathode ray is really a stream of electrons. So what he did was he turned this on and allowed a stream of electrons, which is our cathode ray, to pass through this tube, and then he applied an electric field so that we had a positively charged electric field here at the top and a negatively charged electric field down here at the bottom. Well, what he found out when he did that was that the electrons, the cathode ray here, was repelled by the negative pole, and it went towards the positive pole, was attracted to the positive pole. So we know electrons are negative particles, so that should make sense. The negative is going to be attracted to the positive, and it's going to be repelled from the negative end. So, using some of his experimental data, J.J. Thomson was able to determine the charge-to-mass ratio of an electron. So E here is the charge on the electron, measured in units of coulombs, and M is the mass in grams. So you don't need to know this specific value here. You just need to know that J.J. Thomson was the one who determined the charge-to-mass ratio. So the primary goal of this cathode ray tube experiment was to start to understand the structure of an atom. So J.J. Thomson used what he had come up with to try to come up with some model of the atom. And what he came up with was what we now refer to as the plum pudding model. And we refer to it as the plum pudding model That's what J.J. Thomson thought was there was this cloud, which we have here in blue, that has this diffuse cloud of positive charge. And then we randomly have some negative electrons that are embedded here. So we're going to find out exactly why that doesn't really work. But we call this plum pudding because it looks a little bit like what plum pudding is, where you would have the pudding with little plums scattered throughout it. So the electrons are kind of scattered like plums would be. So later on, Robert Millikan did some more experiments, and he did an experiment using charged oil drops. So what he did was he set up this device here, and we had oil drops that come down through this chamber. And the top of this chamber is an atomizer. So the oil drops come down and they're sprayed into this chamber. And then in the lower chamber we have X-rays that are passed through this chamber. And that ionizes these gas molecules and removes the electrons from them. And those electrons are picked up by the oil drops. So if you adjust the electric field here, you can change the mass to charge ratio on the droplets. Since you already know the mass of the droplets, then you can use that to calculate the charge on the droplets. And once we know what the electron charge is, we already know the ratio, the charge to mass ratio, so then we can use that to calculate the mass of an electron. So the mass of an electron was calculated to be 9.11 times 10 to the negative 31st kilograms. So a pretty small value. If we made this decimal over one place, we would still have to put 30 zeros in front of it in order to write this number out and take it out of scientific notation. So that's a pretty small mass, and we're going to compare that to protons and electrons later on. Sorry, to protons and neutrons later on. So later on, Henry Becquerel did some experiments, and we learned about radioactivity. So what Becquerel did was he had a mineral that contained uranium, and he would put it over some photographic plates. And initially he was doing this on the windowsill so that the sunlight would hit the uranium and produce some images. But then eventually he was doing his experiments and there were a few cloudy days, so he just stuck his plates and his uranium minerals in a drawer and just kind of forgot about them until the cloudy days had passed. And because there wasn't any light, he was thinking that there wouldn't be any images. And then he took them out of the drawer, and he went ahead and developed the plates anyway, even though he didn't think he was going to find anything. And what he eventually found, once he developed those images, was that he found that the images were actually more intense than they had been when he was doing it in the presence of light. So what he found was that he was actually able to get some images, and he actually got better images in the dark. So this led to the discovery of X-rays. And we also learned about different types of radioactivity. So gamma rays, which we're going to talk about more in a later chapter, are actually high energy light. They're actually a form of electromagnetic radiation. Beta particles are just high-speed electrons, and we sometimes write those as instead of beta. Alpha particles are actually a helium nucleus with a 2 positive charge on them. So So later on, Weatherford's two graduate students, Geiger and Marsden, were the ones who actually did this experiment. And what they did was they set up this gold foil with a thin metal foil around it, and they set up a source here that could send a beam of alpha particles at this gold foil, and then they looked to see how those alpha particles scattered around this foil. So if the atom had been the plum pudding model like J.J. Thomson postulated, then what should have happened was the electrons should have gone straight through with only some minor deflections as they move through this plum pudding model. But what they actually found was that there were quite significant deflections. And those significant deflections came when the alpha particles hit a nucleus. So they would hit a nucleus and then they would bounce off to the side, or they would bounce off and go down. Some of them only had minor deflections, but some of them had much larger deflections than you should see if the plum pudding model was correct. So what Rutherford's experiment showed us was that the atom is mostly open space. He found that a lot of these alpha particles pass directly through the foil. And he also found that, as we showed in the last slide, a lot of those particles were deflected at fairly large angles, which would make sense if we think about the atom as having a positive center, because those alpha particles, remember, alpha particles have a 2 positive charge on them, so they're not going to be attracted to a positive nucleus. They're going to bounce off and be deflected from that. And then some of the particles actually got reflected back in the opposite direction. So what Rutherford and his graduate students concluded was that the atom has a dense center of positive nuclear charge, a dense center of positive charge, which we call the nucleus, and then we have electrons that move around the nucleus at a fairly large distance. So we will stop here, and we will talk a little bit more about the atom in class, and then we'll continue on throughout the next few videos.